Ladies and gentlemen, Brandon Young, how are you, sir?
I'm good. How are you, Vaughn?
Oh man, it's been a while since I've seen you. You've been busy.
Busy.
Good.
Busy. Yeah.
You were in town for Power Gen. Thank you for coming by the shop.
Yeah. Power Gen was good. Yeah, a lot of good sessions and here at the shop today.
Yeah, you got a chance to walk around and take a look at the fans that are out there in the shop.
Yeah, you got a few big ones out there.
Yeah, those are shipping out this week. That large skid going to Oklahoma. 300 horsepower hot gas fans on there. That's a beast.
Yeah, that's quite the skid. I think those are some of the largest hot gas recirc fans we've done for you guys.
Yeah, and you've been supporting Vector with hot gas fans for, I believe, almost 20 years. Is that right?
Yeah, I think it's been about 20 years.
20 years. And I've known you almost 15 years. I remember years ago, probably 2016, we went to Amsterdam to look at a fan issue that was going on. And what was the name of that place we went to?
I don't remember the name of the place.
I remember us getting the scariest looking fish for dinner.
Yeah, we walked in and I think one of us said, "What the heck is that?"
So it was a Z Duval, which is Dutch for sea devil, and it was a monkfish. And turns out with a little bit of garlic and butter, it's not so bad. But man, it looks like the angler fish from the depths that they were trying to service today's catch in that restaurant. But anyway, I remember us going over there and looking at problem fans and proposing retrofit solutions. That's one of the things we've been doing here at Vector is working with plants that have had some older fan architecture that's in place, and they've been struggling with a variety of issues over the years. And we've been working with you guys on developing solutions that we can propose to our customers and solve their issues. But I wanted to talk today, since I had you here, to talk about how you go about the sizing process of some of these hot gas fans that we utilize.
Yeah, so I mean, it's pretty simple on our end. We need to know flow, we need to know pressure, we need to know operating temperatures, densities as well. We can help with that, but often we're given the densities, operating temperatures as well as design temperatures. So in your case, hot gas recirc fans tend to be on the lower flow range.
Yeah.
So where centrifugal fans tend to be in a certain specific speed, it has to do with flow and pressure. This is on the low end of that. So low flow, higher pressure.
Yeah, we're talking like 2 to 6,000 ACFM, give or take.
Yeah, that's about right. Sometimes we get up into the 8 and 10,000.
Sure.
But with that flow range, typical centrifugal fans have a characteristic pressure curve
Okay.
that has a peak in it. And at low flow, you can get into certain situations with surging. So the fans that we tend to supply for this application, they have a different characteristic curve that doesn't have a peak. So basically at the low flow condition, we can meet that without having any problems with surging or an aerodynamic instability.
Okay, so with that, these fans not only have a elevated temperature, but also the need for a lot of static pressure. So
Yes.
how do we overcome? It is on the lower end of flow, but from the blower standpoint, it's pushing a decent amount of pressure through it.
It is.
Yeah.
Yeah, relative to flow. So what that usually ends up meaning, or what it does end up meaning for this application, is a narrow fan wheel
Okay.
at high speed.
Right. I think we are 3,600 RPM for most installations.
3,600 RPM for most, sometimes 3,000 RPM if it's going to a 50 hertz application.
Okay.
So, yeah, fast fan rotor, 3,600 RPM, 3,000 RPM. To develop that pressure, you need that tip speed.
And one of the things with that higher tip speed, we're spinning a fan that is seeing a wide temperature range, and we're spinning it very fast. So one of the things that we try to eliminate or mediate is the vibrations that that fan sees. Our specialty is on the process standpoint from how much dilution airflow we need to do a heat transfer with our ammonia and then adequately distribute it downstream. But as far as designing the fan to achieve what we're looking for, you guys have to be worried about vibrations and all sorts of things. How do you guys mitigate that?
Yeah, so vibration, temperature, the high speed of these fans, all big challenges. We build some very large fan equipment. These are not the largest fans we build. If you just look at the fan, you might say, that's not a difficult application. But it is. It's a very challenging application, high temperature, high speeds, vibration mixed in. So it's been a bit of a development process over the years. Go back 15 years ago, we had it would look much different. The fan equipment would look quite a bit different.
Yeah, it looks very beefy and reinforced now.
It is, yeah. And one of the big things was there was a time where we would supply some pillowblock bearings, grease lubricated. Temperature and grease sometimes
Changes the viscosity.
there are issues there. You can cook the oil basically out of the grease. We have other things that we've built in, like shaft sealing and heat mitigation.
Right.
But we also have standardized on a tunnel bearing. And that bearing was offered by a bearing supplier years ago, and they were going to discontinue it. So we actually bought the product line. So that is a Robinson, we call it the BLO tunnel bearing.
Okay.
And if you see one, it's
a tank.
It's a beefy design.
Yeah. 'Cause you got the two bearings, which used to be grease lubricated. Now they're in a central housing, and it's filled with oil.
That's right.
And so they're continuously lubricated. And then, you're dealing with stresses on the bearings because you've got heat from, potential shaft seal leakage, but you also have the conductive heat down the shaft. You have the radiant heat of stuff around it. And you're trying to kind of solve all of that, but also have a reinforced core bearing, if you will, and things like heat flingers and insulation
That's right.
design and all these things are to protect what is already a pretty strong design with the bearing.
That's right. That's right. And the way that you still have two bearings. If you don't know bearings and you look at it, you might not know what's inside, but there are still two bearings in there. And the way everything's machined, it ensures alignment, and with the casting, with the design of the bearing, it is more resistant to those types of things, vibration and temperature.
Yeah, and it still can grow thermally and float.
It can still do what it needs to do from a thermal expansion standpoint.
That's cool.
Yeah.
Yeah. And Vector's been using them, I want to say, for 15 years, that configuration. One of the things in that time is the interface between the skid base itself, the base structural steel, and the fan itself. I can remember early in my career, it was standardized to where the skid cavity and the fan housing were motor bearing pedestal, rather, were filled with concrete to add mass and basically tie the structure to the fan bearing housing or bearing pedestal.
Right. There were some growing pains. We'll say that. There were some times where we thought, okay, there's a little bit of vibration here. Let's try adding mass, or let's try adding stiffness in different parts. And so, eventually we settled on the design we have. We do have some vibration isolation, and again, with that bearing, it has been a very reliable hot gas recirc fan. I'm going to take a step back here. I kind of cut my teeth on field service. Mm-hmm. And I talked about this being a challenging application. I got more phone calls about hot gas recirc fans than any other fan that we built.
Yeah.
So working that customer service side and that field service side, as we started to standardize on certain things for this type of a project, I witnessed
That evolution.
the somewhat unreliable to the reliable
Sure.
side. So it's near and dear to me because I got less phone calls,
Yeah. Well,
less complaints, and
there was a point in my career as well where I dealt with numerous phone calls from the field for similar type stuff, but it wasn't always the fan. Like we talked about how the evolution of the fan bearings and the shaft seals, heat flingers, all these design features and benefits to help promote reliability in the fan package itself, but also the design evolution of our skids. We use tube steel or W members that get coped, but there's only so much stiffness you can add before you get towards that natural frequency of the motor, and your vibration becomes more and more evident. And then, like, even the piping changes, like whether it has a check valve versus a damper versus a tight shutoff valve, and what that does to your standby fan that needs to start in case of a reliability failure. But in turn, that standby fan is the one that's taking the punishment from any gases that are shared between the two operating fan and the standby fan. And so it's a process standpoint where you may look at it on a P&ID and say, okay, well, we need to isolate this piece of equipment. And then Robinson's been very focused on how to make that equipment more reliable, even when there's outside stresses like piping forces or structural harmonics and vibration between the elements. You guys have tried to make your fans more resilient to that, while we've been trying to also handle things from a process design perspective and manufacturing perspective of what is practical and best practice for how we design our structural steel to tie together the skid and make it less susceptible to vibration, and how we do our piping design and where we put a check valve in lieu of a tight shutoff valve in order to make sure that the fan and the equipment is protected as well.
That's right, yeah. And there's been advancements there as well, changing those things like you said. When you're dealing with these temperatures, these are high temperatures, some of the design temperatures up to 1,000 and above. The fan that's moving air, it's moving hot gas. There are components on the fan that help with cooling while it's operating. So you're right, yeah, the standby fan, without having certain components within your piping,
Yeah.
that standby fan sometimes was seeing some very high temperatures.
It's another reason, you're talking about like the standby fan being idle and not spinning, and instead it's heat flinger that rotationally would help remove heat from the bearing. Even though it's off, it's still getting some of that heat from the process, and that's
right.
conducting down the shaft itself and putting some heat into those bearings, even when this fan is not in operation. But when we're talking about the fan design itself, what makes the most sense in terms of reliability and readiness, if you will, for that standby fan? Years ago, people used to pipe the drains together from one fan to another, so there was shared interstitial flow or radiant heat to avoid corrosion, condensation forming, and so forth. But what do you guys kind of recommend there? Do you want your fan just completely isolated from temperature when possible, or?
Yes, I do remember that time frame where we tried some different things. One of the things that we do with a hot gas recirc fan is all of the fan rotors are built from stainless. Years ago, we used mild steel, and we would see a little bit of corrosion here and there, and sometimes, believe it or not, that would affect balance.
Sure.
From time to time. So most of the time with these fans, we're looking at a 300 stainless, but with some of the very high temperatures and the high tip speeds, wheel stresses will push you into like an Inco material,
Okay.
stronger material, like an Inco 625.
And that's pretty corrosion resistant material.
Yep.
It's kind of like a stainless.
I'm not a
in that regard.
materials expert.
I'm not either.
But yeah, we've had really good success with the 300 and the
High
the
nickel or high chromium, something like that.
Yep.
And those stay very balanced, but it comes at a cost to the fan, right? It's more expensive.
It does, and yeah, it's worth talking about because you may buy a fan for application A, and you think, you're adding a little bit more flow and a little bit more pressure. Why is Project B's fans? Why did they go up 25%, 30%, whatever that looks like? You will get to that point where the stresses in the fan wheel are high enough that pushes you into an Inco 625 material, and I haven't looked at pricing lately on those specific two materials, but it's quite a bit different. I think Inco, you're into the $30 a pound range.
Is that right?
Yep. So yeah, just to be aware, if you guys are comparing A and B, apples to oranges, there's a reason behind that, and we're happy to have that discussion. Why did the price increase?
Right, right.
But yeah, it often has to do with material.
And one question I had was, you've seen a big uptick in motor pricing recently, is that right?
Yes, I'm not into it day to day.
Right.
But yeah, motor pricing and lead times.
Yeah, I mean the motors and so forth, especially coming from overseas, it's been a challenge. We're yet to see impacts of any tariffs or any discussions like that going on, but I would suspect, I don't know where Inco materials are made domestically, but I imagine it's going to add to the cost figures as well.
Yeah, and we're still in the early parts of that, so we're still trying to work through, what is that going to look like, not just for us, but for everybody, right?
Right.
So
It's going to be across the board impact.
Yeah, we think they're going to want to source materials from here because there are now tariffs for, but that's going to drive up U.S. demand.
Yeah,
So,
and then the cost, economics from there.
yep.
Well, that's good. You guys are in a lot of different industries than just power, but what would you say is your largest industry that you guys support?
Oh boy. Well, we're pretty well diversified. So that's kind of a hard question because it shifts too, right?
Sure.
Right now we're seeing, we just came from power gen, data centers, AI. In the power industry, we're expecting a huge uptick.
As are we, yeah.
Yep. One of the ones that I would name is cement. We do a lot of work in cement. We do a lot of aftermarket work.
Oh, like retrofit and repair?
Yeah, hot gas research application. Sure. You're not dealing with wear. So, and it's when there's dust in the gas stream and things like that, like in a cement plant, those rotors wear out.
Very abrasive and so forth.
Yeah, and we try to design in certain things, whether that be hard surface materials or, maybe even looking at a double width fan instead of a single width fan, so you can, move less air and less dust through certain components. But we are really diversified. Cement, pulp and paper, drying equipment, ethanol. It's been, we've been around for over 130 years, and different industries have gone up and down. So being that well diversified, it's helped us survive through some tough times in certain industries, right? If I can talk a little bit about
please.
that. So we were founded in 1892, and we sort of started off making parts for mining equipment and mines, and very quickly became a ventilating company, and we were called Robinson Ventilating Company. And it was primarily for the coal mining that was happening in southeast Ohio, West Virginia, and western Pennsylvania.
Where you guys are located?
Where we're located, where we're headquartered, we have operations, we have manufacturing in Pennsylvania. That site, we've been there since 1921.
Wow.
And then sometime, I think it was in the 1970s, we set up shop in Florida. And then in the 90s, we opened up manufacturing in Utah. We have a service outfit in Alabama. And we have some service guys that are placed around. And then we actually purchased the machining and fabrication. We call it Robinson Machine, but they don't just do machining. They fabricate tanks and vessels and some other things like that, kind of like you guys do as well.
Sure.
But yeah, very well diversified. We started as mine ventilation, and then over the years with process fan equipment. If air needs to be moved in heavy industry, we've probably supplied a fan.
That's kind of a parallel to our slogan of any process, any fluid, we can design a system around. So yeah, that definitely resonates with us as well. And we're using, when we have to move air or a vapor or a flue gas, hot air, we're using a fan like yours as part of a intricate system to supply ammoniated flue gas.
Right. You probably, I can imagine your equipment, has its range where it fits well. Mm-hmm. Meaning, let me rephrase that. Maybe a very, very light duty application might not fit you well.
Yeah, that's
because
true.
you build something that's a little more heavy industry.
Right.
And we run into that too. Our wheelhouse is heavy industry, heavy process. When you get down into HVAC and that type of
Lighter duty fans and so forth.
yeah, we don't really play in that market.
That makes sense. Yeah, I mean, same with like tanks and so forth, where we specialize is either really big anhydrous tanks or anything stainless on the tank side. It's just where we fit in the market.
For sure.
Now that's good to know. And like you said, there's some industries that have been legacy industries for your area, especially coal, mining, those type of things, ventilation, but all very heavy duty, very robust applications, I'd say.
Definitely, yeah. And it's interesting, because that industry that allowed us to become a ventilating company, and you see those sometimes industries go away, right? Not as much coal mining, of course, not like there was in 1892.
Sure, yeah.
So
there's going to be some deregulation. I don't know if there's going to be that much deregulation in the power market. I think it's largely focused on natural gas, and even some talks of fuel blending with hydrogen are kind of losing some of their momentum this year just with the administration change. But
yeah, there's still a few coal plants that are operating out there, but there's interesting discussions. Hey, this coal plant that's been mothballed for X amount of years, they're talking about starting it up again. I don't know that they're going to be using coal. I think they're the conversions from coal to gas in those types of plants, but they do still have some of the infrastructure there and some of the components. You just need to make steam, right?
But I mean, that's at the end of the day, whatever heat source makes the steam is what your power source is, whether that comes from, the sun or nuclear power or a locomotive. Right. At the end of the day, your aim is to get steam, and what's the most efficient way to do that?
That's right. But of course, it's not just steam turbines. Primarily for the hot gas recirc type fan. That's going into a combined cycle or a simple cycle plant, where they're using an aeroderivative gas turbine. But often, if combined cycle, use the waste heat in an HRSG, make steam, and then you make more power with the steam. So
or cogeneration, and you're using the steam to heat a hospital or provide to your host plant for some other process. But
that's right.
Yeah, and you brought up you do well in heavy industries. There's a sweet spot where a hot gas fan in an SCR application really comes into its own, and there's some arguments to be had there. But when it's lower ammonia flows, we don't need a larger horsepower hot gas fan we can do it with electric power. At a certain point, that power demand of vaporizing the ammonia gets so great that using, like you said, a waste heat stream with the hot gas fan, like a Robinson, that we would utilize that for the vaporization in the diluent media. So, where that threshold is got a different sensitivity depending on the application. If a plant's making a lot of power, well, maybe a half a megawatt to vaporize the ammonia is not such a big deal. But chances are, right at the point where kilowatts or start equaling horsepowers of hot gas fans is where you'd want to kind of focus. So, where we're 350 plus pounds an hour of aqueous ammonia, that would put us into a reasonable size electric heater where you're like quarter megawatt or maybe slightly less. Okay, well, at a quarter megawatt, suddenly a 75 or 100 horsepower fan is less of a burden than the electric resistance heater would be.
Right. Right. And I don't really know where that threshold is.
No,
That's up
but
for
for
you to
us,
figure out, right? Whether you're going to be using an ambient air fan,
sure.
pulling ambient air, and then heating it with that electric heater.
Well, and
Most of our supply is in the hot gas recirc.
absolutely, but where I'm going with this is like on a retrofit basis. We'll work with the customer to say, hey, based on your process and your flows and your existing fan, this is what we're recommending. People's like, well, Vector doesn't make fans, so why would we go with Vector? And it's like, yeah, but we make the thing that the fan sits on and plugs into, and we can verify the performance of that fan, and we're giving that process data to Robinson to size us what we're looking for. And then also the interface with the piping, the interface with the skid structural members and where it lands and bolts down to the equipment. So figuring out the mechanical interface and the integration to the SCR system, that's where Vector kind of comes in really clutch with these retrofits. And we're able to kind of back calculate out from their process conditions what the desired dilution airflow should be, because oftentimes you go look at the flow meter in the field and that fan has lost some of its ideal flow at that point over the years due to fouling or whatever. So, we kind of specialize in that integration and shoehorning or retrofitting a better, more robust fan into existing applications that maybe predated some of these design features in their original installation.
Right. And, Robinson has done some of those retrofit type situations. It's not a new skid that we're shipping fans to be installed on if it is a retrofit situation. And that varies too. We've seen different versions of that. We may design the fan just as we would design it and ship it off, and it's up to yourselves or someone else to figure out
To make it all work.
how to interface the piping and where we got to move the valves. And but in other situations, I was involved with one out west one time. We actually were able to take some design considerations, center lines of piping, inlet and outlet piping, and maybe match that. Maybe even supply transition that helps with that. But I think each one's different.
Oh, every one.
Each retrofit is different. So
That's what makes them fun, though. Because if we look at all the variety of fans, they largely fall into like 5, maybe 6 sizes of fans, and then horsepower dependent. But when you're talking about shoehorning in a retrofit, the standard off-the-shelf, make model isn't going to plug in. It's the custom application, and that's where working with you guys has been super helpful in us saying, okay, well, we went out and took measurements, or here's the drawings, and the customer's trying to minimize this outage work whenever possible. How can we make this as turnkey as can be?
right, and our engineering and design team drafting, we can certainly work hand in hand with a retrofit situation to try and see if we can make that a plug and play. But you're right. The fun of it sometimes is how do we make this work? And you're dealing with engineers and design people.
And then what is in the field often doesn't match that.
Yeah.
You know.
Right. When you talk about shoehorning in a fan or let's say footprint, right? Our hot gas equipment, our hot gas fans that we supply for this industry, they're all direct drive. So it's fan rotor, fan shaft, bearing, coupling, motor, all in one line. We have run in and have seen from time to time belt-driven
Sure.
fan equipment out there. So at the end of the fan shaft, they'll just have a belt pulley and a belt drive, and you may not have that real estate on the back end of that because the motor's mounted on the ground and you have this belt drive system. So in those cases, we do not design any of the hot gas equipment to be belt drive.
Sure.
So we would want to be talking about, is there room for a direct drive fan? Can you make modifications to the skid to allow for that? So it's just a few design.
Adjacent real estate to the concrete area, like all that gets looked at.
Yeah.
And you're right. I mean, we've even seen where the most economical way to do an installation may not look the best, but putting in a small maintenance pad to mount the fan to off skid and pipe over in some instances, we've seen that done.
Yeah, and doesn't matter for us, right? We if you want to mount it off to the side and change your piping so that you can get those hot gas fans in there, doesn't make any difference for us. You guys are good at designing that type of a solution, and we just care about flow and pressure and temperature, right?
And we are looking at all of those things as well, but also the mechanical and the constructability aspects of it. Like, we need to heat flue gas from X to Y, or we're taking X temperature flue gas and we're dousing it with ammonia and it's leaving at a different temperature. But then it's the actual mechanical construction of it that sometimes is the limitation. We've had a few projects recently where they had to fit in a shipping container, and that's changing the whole layout of things. The big ones we looked at today when we walked out in the shop, those are 300 horsepower fans. Those are the largest research fans we've done. That skid is going for an advanced Class J-class turbine. And it's 300 horsepower hot gas fan, and the outlet of it I think is like 14 to 16 inches. It's a huge fan for this application. But now we're into equipment that's so big, we've got to disassemble it to get it out of our shop, to put it on the back of a truck and ship it down the road. So the new build stuff is very interesting in that regard, but also the retrofit opportunities present a unique challenge that we're kind of excited by on a regular basis.
Yeah, those are big ones. 300 horsepower. Some of what you just said, it was a foreign language to me, so I don't know what Class J and all that is,
so these are like the newest, biggest gas turbines that are out there. If you've heard,
okay.
So if you're used to hearing 7F, that's an F class. I'm going to be going to the 7HA users group. Hopefully speaking at that with the advanced class turbines, as I was familiar with those projects when they were new. And now they're getting to be old enough that they're starting to need emissions controls help on the backstream side, on the exhaust side. Okay. When we're talking about these big ones, a J-class turbine makes upwards of 6.5 million pounds an hour of exhaust flow. And if you're talking about that in simple cycle, now you need cooling air fans to round that off to about 10 million, 11 million pounds an hour of total flow through this, because you're adding in all this ambient air to cool that large mass flow of exhaust down from around the 1,000 degree mark down to the 850 degree mark on those simple cycle applications. So the slipstream that we're utilizing to vaporize the ammonia for such a a big gas turbine, that slipstream is now on the high side, 12,000 plus ACFM of hot gas that your fan's moving. So that's quite a bit of flow through that piping that we're utilizing to dilute the ammonia and vaporize the ammonia, send it downstream to the AIG for distribution.
Yeah, and we have seen over time, makes a little more sense. I now understand you were referring to the class of turbine.
Yeah, I got wound up with the turbine user groups that we've been going to, where you just start throwing out the call signs of these engines.
Yeah, right. But to talk a little bit about that, we continuously see, not continuously, but seems like steps, right? The biggest fans that we've built for a hot gas application, well, why is that happening?
Right.
And it makes sense that you just need more flow.
And the sources of power, because of the turbine technology, keep getting bigger and bigger and bigger and flow more and more. And correspondingly, the emissions control system with its fans and pieces of equipment get larger and larger with that scale as well.
Right, and as we've seen that progression from this higher flow, or whatever pressure you're talking about, but flow, the fans getting bigger and bigger. Yeah, there have been design challenges along the way. Again, with the materials we talked about, when you start getting into higher fan performance, you start getting into bigger fans. You start getting into higher tip speeds, higher stresses. So that'll play into your material selection as well.
When we're talking tips or rotor diameter, I think 44 in that range, 44-inch diameter, tip to tip, that seems to be the largest that I can think of.
Yeah, that's about right. I'd say we're anywhere in the 20-inch range, but that's definitely on the high side.
Do you think we'll see a 50 or a 60-inch wheel if things keep getting bigger and bigger, or are we now facing a new design challenge at that threshold to say, okay, well, we can't go any wider, we can't go any taller, or what comes next if we have to get more and more?
Right. Yeah, my wheels were already spinning as we were talking through that. And that is interesting.
All puns intended. With
yeah,
the
yeah.
wheel.
My fan wheels were spinning. Yeah, yep. Yeah, that's an interesting question because I can imagine a few solutions that might look different than what you have.
I could see us getting to a point where the stresses or the speeds get so high that you're now into either different rotor design or different materials even. I don't know what the Inco material stress limit is, but I would imagine we're going to reach another design evolution as the turbines get bigger and the ammonia demand gets larger and the corresponding skids get larger. What does that look like from a fan sizing? We're going to reach another limitation, I would think.
Yeah, so the fan design that we typically use, it has some inherent design characteristics that actually it is low stress, and as we start to get into bigger or higher flows, essentially the fan wheel has to get wider.
Okay.
Or the fan rotor, whatever you want to call it. It has to get wider, and when you start to do that, then the stresses, they change, right? Mm-hmm. So actually, if you get up into the 20 or 40,000 ACFM, I don't know where we're going to end up. It might mean two fans in parallel.
Right? Now we're talking.
So if you need 20,000 ACFM, and we're getting out of a design range at 3,600 RPM, it very well could look like two 10,000 ACFM fans or two 15,000 just to meet that flow. Okay. When I say in parallel,
no, I'm
basically
with
you have piping that splits, goes through two operating fans, and they each offer that amount of flow, if that makes sense.
It does. In fact, to your point, I think we get to a certain size where we need a skid on each side of the unit, where one skid with two big hot gas fans on it is only feeding half of the
Oh, yeah.
exhaust system. We've already seen some of these advanced simple cycle designs. The width gets to a point where you can't do that with a span of AIG lances without them sagging, right? Because of the distance of,
Oh, right.
of the piping.
Yeah.
So now you're into several supported zones of adjustment to put the ammonia where the NOx is in the exhaust duct. But to your point, we may need to feed on either side of that unit a dedicated skid with two fans that are only running at 50% of the total flow, because now we're into such big ducts and we have to distribute all this gas and everything else. It's a design challenge, and more of these bigger units are coming down the pipeline for data centers and other power demands.
Right. Yeah. And what does that look like then? Because in this application, we supply two fans typically, right? So we have a redundant fan, that idle fan, and it's there because in a pollution control situation, you have to have a backup.
Absolutely.
If fan one goes down, fan two has to be ready to come up. If we're talking about two fans that are operating to get the flow, well, then you have to have four fans.
If you need that same level of redundancy.
Right. And then,
But then
like you mentioned, maybe it is four fans, but maybe not on the same skid. Two on the west side, two on the east side.
And the equipment's going to get so much bigger that you run into a skid now at the limits of shipping size as well. You know what I mean? I can imagine if you
Yeah.
double the flow, your fan's going to get much bigger from an envelope size perspective. And now you get into how big of a skid can we actually put this thing on and still have it shipped to the job site?
Right, right. And if it's going overseas, then
Yeah.
these fans for us are relatively on the small end
Of what you build.
of what we build.
Yeah.
And for an Arrangement 8 assembled fan, so we don't really have to worry about those shipping concerns. That's for you to figure out.
For sure. I just think, to that same conversation, things are going to progressively get larger and larger. And technology is forcing the market that way because of more and more power demand.
Yes, it's going to be interesting. It's really where does that cap? Where does that cap?
Yeah.
And with the data center side and the needs there,
It's only data.
instead of having a huge class whatever,
Right.
maybe it means a bunch of 40 megawatt turbines, right? Instead of continuing to grow that turbine size, it's going to be interesting in the next.
Yeah. Are you
Some
powering
people
a city?
say 5 years, but it's going to be longer than that.
And it depends. You're powering a city, or are you powering your set of servers or processors that you're doing?
Right.
And you're peaking those as demand rises.
Yeah, and we're hearing some of the data centers are getting so big that they're talking hundreds of megawatts. So it's a lot of power that's needed.
Yeah, we're doing a data center project right now out in Abilene, Texas, and we're doing the ammonia systems for that. And they're two big 20,000 gallon ammonia tanks to feed 5 engines that are just peaking power for them to do this data center. So that's the one that was referenced on the news with the Trump town hall or whatever.
Right. Yeah. I heard it was in Abilene, and I just wondered why Abilene.
Well, I think that's where the West begins. You start getting into non-attainment zones beyond that for emissions and so forth. But it's probably permitting.
Yeah. That's a good point.
And as that deregulation changes with the new administration, there's going to be more and more opportunities for things to be built.
I just found it an interesting place. We used to manufacture in Abilene, and there are other reasons that I've been there. But when I heard Abilene, Texas, I thought, wow, that's an interesting place for technology and
True. But it's remote enough.
It's 3 hour drive from Dallas,
DFW, yeah.
Or you ride in a plane that's this big. It's not really easy to get to.
True. It was right off 20 there, but I think it comes down to cost in that area, and it's remote enough that the neighbors aren't complaining about your new data center buzzing, and then also the deregulation, because fewer population density out there. But anyway, well, let's wrap this up. Thank you for coming by. Hopefully Power Gen was good for Robinson.
Yeah, it was good.
Valentine's Day is tomorrow. Don't miss that.
I already celebrated mine.
Good,
So, yeah.
good. We got Vector Vipers softball practice tonight. Too bad you're not sticking around for that. If you want to hit some softballs in the batting cages with us, you're more than welcome.
Is it indoors?
It is.
Because this isn't the weather that I ordered when I came to Texas.
It is
I'll tell you that.
38 degrees. It was 21 this morning. That is not McKinney, Texas weather for this time of year.
Yeah, I came from Pennsylvania, so I was hoping for.
You did
Yeah,
not.
hey, I'm heading south, right?
Yeah, I think you're going to have to wait until some of these upcoming users groups where they go to temperate climates. Are you going to any other shows coming up?
This year is a challenge for one individual, so we're sort of dividing and conquering. There's actually 3 shows that are going to happen all in the same week.
Okay, cool.
Petroleum, cement, and steel. So,
Wow.
So we have different Robinson people going to those shows. But yeah, we also are going to do an ethanol show in the summertime and
Nice.
looking at a few others as well.
That's cool. Yeah, we're going to do Western Turbine. We've got the API show. We've got the syngas and nitrogen conference, and then we're doing the biogas. I think I'm speaking at biogas. Some market diversification there, but primarily power. Well, Brandon, thank you again for coming in. I appreciate you taking an hour out of your day and meeting with us. I know the podcast thing's an odd format, but I think it went fine.
Yeah, for sure.
Okay.
Yeah, anytime. Appreciate
Awesome.
it.
Well, good, and safe travels home. Appreciate you joining us.